Last time we discussed upcrossings of the by the stationary process some level, and we get a very simple, nice formula for number of upcrossings. This formula became to be much more simple in Gaussian case. Let me recall Rice formula. We considered stationary Gaussian process. And discussed the following question. Suppose that we have fixed interval 0, t for example, and then we discuss how often process psi will do the following thing. Will intersect the level u from below to above. So this one, and we get a nice formula which looks like following. Suppose that expectation of psi t is equal to 0, and variance of psi t is equal to 1. Then the expectation of this number of upcrossings of the level u have a form. This is some constant multiplied this constant came from square root of 2 pi, which is present in the probability density of psi t, and also from the expectation of positive part of its derivative. It must be noted that in the case we have Gaussian process, its derivative, Gaussian stationary process, its derivative and process at the same moment of the time are independent. So the formula begins to be like this. And for us, what is important? You see here the value of Gaussian density, and at the same time, this is more or less the way the estimation of Gaussian tail. We will see. So one can see that probability that psi t is greater than level u looks like expectation of this number of upcrossings up to the constant c. This idea can be transformed to arbitrary Gaussian random field with multi-dimensional parameter, not only with one-dimensional parameter. But in order to do this, we need to understand what is the meaning of the number of upcrossings for multi-dimensional case parameter t. So we discussed this last time and agreed that instead to calculate upcrossings, I can calculate this intervals. This is for smooth trajectory. This is the same. Yeah? And instead of number of occurrences, we have number of such intervals. And we produce the following definition. We define Euler characteristic for one-dimensional set as follows. If we have one-dimensional set consisting of intervals, finite number of points, and finite number of intervals, then we just calculate all these subjects and say that its number is by definition Euler characteristic of the set if it is the set A of the set A. We see that more or less Euler characteristic gives us imagination how many parts contains the set A. But in one-dimensional case, it is relatively easy to define parts. We already said that we just consider special sets, not arbitrary, but special sets, such that they consist of a finite number of intervals and finite number of points. Then we just say that the total number of these subjects is Euler characteristic of the set A. But what we can do in general case? In general case, we will proceed as follows. Now let's take dimension equal to 2. And I will suppose that the set A is a finite union of closed convex set. So it can happen that A, for example, has the following form. This is example of the set A, just one convex set. For such one, because this is also convex set, and so on. So we can see that this is more or less rich family of the subsets of the planar Euclid space. Now let us try to define Euler characteristic for such object. We can do it as follows. Suppose that we have coordinate system here, and then let us take let us draw vertical lines and consider vertical sections of our set. Here, here, and so on. So you see that due to our assumption on the structure of the sets which we consider, we will have in the section, we will have exactly the sets which we discussed before. So every such section will consist of just finite number of intervals or finite number of points. Then one can consider, for example, this will be a point X, and this section I will denote it by A with indices X. Then one can consider Euler characteristic phi of AX. As we discussed, this is just integer valued function of the point X. More one can easily check that it will be a step function. So the picture of the function of such kind will be like following. We have 0, then one step, another one, and so on. For convenience, as we are probabilists, so we can just say that it is continuous on the right, but it does not. Then what we can do, we can just integrate. We can just integrate. And then calculate the integral phi AX, excuse me, phi AX. And integral. And we will say that obtained integral is the Euler characteristic of the set. And it can be checked that such definition does not depend on the choice of coordinate system, and leads to functional of the sets which has also integer valued, integer values, and can be used to calculate properties, to check some properties of the set. For example, if we have some set like this one, which consists of 3 non-intersecting open convex sets, its characteristic will be equal to 3. Yeah. Then for such set, A phi of K so one can calculate number of this number of pieces at the level set of the random function. So we now have a function which allows us to speak about the structure of the set of the level set of multi-dimensional random process. I am saying multidimensional because the same procedure can be done for dimension 3. From dimension 2, we have sections for dimension 4, and so on. So we can define finally by induction this Euler characteristic for sets in multi-dimensional space. Then we can consider random field. I will draw a picture for 2 dimensions. For example, this is a graph of our random field, and then take a level U. Consider a section. Then we will have level set of such x. The psi of x is greater or equal to u. And this level set will be like following. Let us consider its Euler characteristic. We already know that such function will exist, and we can define it properly of this set x psi z psi x is greater or equal to u. And interesting result, which in some sense generalize Rice formula, is the following. It occurs that for smooth random field psi, we have the following probability that supremum of psi is greater or equal than u. So probability that we are greater than u is equivalent to expectation of Euler characteristic of this levels. When u tends to infinity. So we can see that one can relate tail probabilities of suprema of Gaussian. Of course, we take suprema on the power of Gaussian random field and Euler characteristic of the levels. And actually, it is not too hard to understand the idea why it happens. I said that xi must be smooth, so continuously differential. And must for this relation holds, we need another assumption that psi achieve its supremum only in one point. This is additional condition that psi has only one point of global mass. We will see the example I will give you an example. But before to consider example, we understand why this condition leads to this relationship. Really, let us consider just one-dimensional case. Here is our interval, and here is the object. Then, for example, at this level, Euler characteristic is equal to 2 of the level set. But when we will achieve the point of the max, if it is only one, we will have only one level. We will have only one interval. It means that from some level u, random, our Euler characteristic will become to be equal to 1. So it will coincide with probability that we are above u. So this is a just simple explanation why it is related to structure of the level set. Now let us consider example when we will have such property that psi has only one point of global maximum. And this example will be from one side very simple, from other side will lead us to the new subject for our today lectures. So I will discuss this property on the example of Wiener process. Because in this lecture today we will begin to study more the Wiener process in more detailed way. So let us consider the following Gaussian process. Wt is greater or equal than 0, such that expectation of Wt is equal to 0, and covariance function expectation of Wt multiplied Ws equal T minima S. This is standard Wiener process, and we usually relate this process with a mathematical model of the Brownian motion. I will not speak about the such model because now we consider this process as an example of Gaussian. And we know that these two things define distribution of W total. So we can understand that we can find any properties of W just using these two objects. For example, let us consider T1, which is greater or equal to 0, T2, and so on, T indexed by n, and consider the differences. W T2 minus W T1, and so on. W Tn minus W Tn minus 1. Then we can check that for any two of such random variables, we have the following property. Expectation, for example, I will take first two. W T2 minus W T1 W T3 minus W T2 is equal to 0. It is very easy to calculate. Then one can say that we have the set of uncorrelated jointly Hauschian groups. We already mentioned that it immediately follows from here that they are independent. So we know now that increments of the Wiener process are independent. Let's write it. This leads to a lot of good properties, and we will see how, of the Wiener process. But I need some more property, which also very easy to have now, namely continuity. We already have different conditions for Hauschian random field of process to be continuous. In this case, the most easiest Kolmogorov condition for continuity works. We have expectation of W T2 minus W T1 square is equal, again, it's very easy to calculate T2 minus T1 for T2 then we see that process W is Hölder continuous in square norm. Yes, we discussed that this is enough for Hauschian case, it is enough for continuity. So W is continuous. To be very precise, I must say W has continuous modification, but we will always use only this modification. So I roughly speaking say W is continuous. Yeah. Now let us speak about its maxima on the interval. Since W is continuous, so when we consider it on the interval, say 0, 1, for example, it must have maximum, like this. But am I right drawing picture in this manner? Because I draw only one point of global maximum. The question which we want to discuss as an example is the following. Can it happen that trajectory of the Wiener process on the interval 0, 1 have two different points of global maximum? So can it happen that the picture will be like forward? This is maximum, and we have this. So we have 2 points of global maximum, 2 distinct points of global maximum. It occurs that no, and let me explain why. Let us take some fixed point, for example, T0, inside of our interval. Then consider 2 new processes. One process will be indexed by S from here, and another one process will be indexed by R from there. Then I will consider the following two processes. One is WS minus W T0 for S belonging to 0. And another one is WR minus W T0 for R belonging to T0. Then one can check from our previous consideration that these are two independent processes. These are two independent processes because we already discussed the increments of the Wiener process on the different interval of the time. Then we can see that assumption that we have here 2 points of the global maximum, one is here, one is here, leads to the following relationship. Maximum of over 0 is equal to max. So to understand that this event can happen with probability 0 for fixed t, we just have to understand the distribution of this random variable. If we will be able to prove that in our case this distribution have a probability density, then of course for two independent variables which have density to be equal, this event can have only probability equal to 0. Yes. So we only need to check that this distribution have a density. Then everything will be okay.
Sorry. Could you could you explain identity? The two marks. Okay. Let's see. Could you explain why these two maximum are equal?
Because now I consider the following case. I am checking that if I fix, this is not the final problem, but I am checking now that if I fix some t0 inside of the interval, then probability that we will have 2 points of global maxima. One is in the left-hand side, another in the right-hand side of t0 is equal to 0.
Mm-hmm.
Yeah. And,
so you have a global maximum between 0 to t0, and you have another global from t0 to 1.
Yeah, exactly.
Yeah, how we know? But if you say, if you look at the two sides minus w t0, we can delete w t0. That means the two global maximum have to be equal.
Oh, yes, yes, I can, of course, I can delete this WT0, but you see what happened? Then we will have only equality. That at some point here, we have the same values, but they will be dependent. They will be dependent. This is the one, and another one we don't know its distribution. Okay? But when I proceed as I did, I have the equality between two independent variables. This is the reason why I am subtracting this WT0. I have two independent random variables, and moreover, we will see very easy that such random variable have a density. And if we have two independent random variables which have densities, they can be equal one to other only with probability 0.
Yes.
So this is the reason why I am subtracting this WT to have independence.
That's right. Thank you. Thank you. Yeah, thank you.
You are okay. So let us check now that such random variable have a density. I will prove it using the very useful mathematical trick here, which is called reflection principle of onion motion. Let us speak about the probability that maximum of the interval 0, 1 of WT is greater than U. U must be so. This is the level U. This is our trajectory, and it can, let's consider when such event can happen. It can happen in two things. One is following: when the final point W1 is greater than U. Of course, then due to continuity, we already remember that W is continuous. Due to continuity, we will cross level U and have such an image. Another one situation is the following: it hits level U, do it as follows, and then go down. Yeah. Then maybe we can imagine that Wiener process is symmetric. So when we consider W or minus W, it has the same distribution. Here I can again apply just Gaussian argument. W minus W have the same mean and covariance. So they have the same distribution. But what I am doing, I will just consider the random moment tau, and this tau is defined by the relation that W is equal to U. If we hit this, if we hit the level U, and maximum W equals U for the interval 0, 1, and tau 1 if this max is now I will consider a part of our process. W T minus W tau when T is greater or equal to tau and less than equal to 1. So if tau equal to 1, we do not move things. Then here we have also Brownian motion. In this point, I am just assuming that after this random moment of time, Brownian motion, Wiener process have the same behavior. This is non-trivial. This is so-called strong Markov property of the Brownian motion. But it is rather technical statement. So we don't prove it here. But I will use it. And from the physical point of view, it is trivial to understand. Yes, when we consider Brownian motion in the isotropic medium, then if we fix some time, if we fix this packet, then consider its trajectory after we fixed it, then we will have the same Brownian motion. So from physical point of view, it is really trivial. But as I said, it must be proved. We will use that this is also a Brownian motion. This is a Brownian motion. Then, as I said, Brownian motion is symmetric. So I can consider the following also. It also be a Brownian motion. Since then, probability that we hit level U and get this point or symmetric point because of the symmetry are the same. Because one can consider this trajectory which is symmetric after the time tau. Finally, we understand that probability that our maximum is greater than U is equal to two probabilities, two, because of the symmetry, that W1 is regular. So we find distribution of maxima of Wiener process and the on the interval 0,1. This is 2 multiply the probability, 10 probability of final point. This is the reflection concept which we noted. And from this expression, I can find density. I can find density for maximum. It's very easy. It is just 2 times density of Gaussian distribution. I even don't need this expression. So we know from here that maxima has a density. Now we know that maximum W has probability density. U, which is equal to 1. Now we can come back to our considerations. We already have a formula that our assumption that we have one global maxima on the left-hand side of the fixed point T0 and another global maximum on the right-hand side of the fixed point T0 leads to this property that such two processes have the same maximum. Now we know that these two random variables have densities, say Q1 and Q2, and they are independent. They are independent. So let's find a probability that these two random variables are equal. Its joint distribution also have density in R2. In R2, joint distribution of these two independent random variables have a density which is equal to the product of these densities. Q1x, Q2y. X, y, so the probability that they are equal is equal to the integral R2. Here is the indicator of the line x equal to y, Q1x, Q2y, dx dy. And it is evident that this integral is equal to 0. Because here is line. Line is one-dimensional. And it has the back measure 0. So when we integrate arbitrary function along this set, we have 0. So we see that if I fix some point, then probability that we have two global maxima, one on the left-hand side, another on the right-hand side of this point, is equal to 0. But we don't know where is this point. How we can proceed? Now let us come back to our general situation and just suppose that Wiener trajectory of the interval 0, 1 have at least 2 points of the 2 distinct points of the global maxima. Like then, what can we for sure can find a rational number T0 rational between two these global maxima. Yes. Because if we have 2 distinct points, we have interval, and every interval contains rational points. So we have the following: the random event that there are 2 distinct points of global maximum. Global maximum can be written as a countable union with respect to these rational points of the interval 0, 1 that maximum of the interval here is W S equal to maximum on the interval T 1 WR. Yes. Now what I'm doing, just subtracting here WT0, WT0, exactly as we did, and then we know that this event have probability equal to 0. Yes, for any point T0. Here we have countable union, and due to this probability that we have 2 points of global maximum is equal to 0. Finally, we get that this probability is equal to 0. So we proved that this is a wrong picture for trajectory of Brownian motion. Picture must be like this one. We have just one maximum. Of course, it can be achieved on the right hand side of it. So we see how Gaussianity and this special kind of covariance function leads to some interesting property of Wiener process. Next lecture will also devoted to much more deep properties of Wiener process, and we will discuss its geometric properties of multidimensional Wiener process. For today, this is the end of the lecture. Thank you for attention.
So, thank you, Professor. So, any
beautiful argument
or comments?
Very smart argument. The last step. So there are 2 global maximums, identical maximums. Then there must be some rational number, you know.
Yes, yes.
Beautiful, just beautiful argument.
Oh, thank you. We will use such an idea a lot of when we discuss Wiener process, you know, because of we have the property of independent increments for Wiener process, but for fixed types, for deterministic types. So to use this property, we need to organize some deterministic intervals. Next lecture, you will see how we will do this in much more difficult situation, but also we will use this trick a lot. Okay, if there are no questions, thank you for attention again, and see you next week.
Yeah, yes, thank you. So maybe not the next week, the next 2 weeks. Yeah.
Yeah.
And yet, you know, the next week is the Spring Festival, so it will be the February 8th. Yeah.
Oh,
February
I
8th.
see. I see. Yes,
Yeah.
yes. Okay.
So thank you, Professor.
So, okay. So you will have a new year next week, yeah?
Yeah.
Okay. So let me congratulate you before this event, but see you at February.